For more videos like this for discrete 1, you can take a look at TRY studies. Link is in the description box below. We're told to prove that if n is even, then n squared is even. How do I know to use if then? Because of this implication operator tells me if this, then this. If you see the word show instead of prove, it's the same thing. Before anything, you have to specify what domain are you working in. Here they don't tell you, but you have to use the context of the problem. You're dealing with numbers that are even, and the only set of numbers that can be even or odd are integers. So that's a fact to keep in mind. And the way we represent the set of all integers is with the symbol, a z with an extra line. The next step, no matter what proof you're doing, is to write down your definitions, because we want to be clear. What does it mean for an integer to be even? Well, the way to never forget is to think, what are the first 3 even numbers that I know of? Well, maybe 2, 4, and 6. And how do I know that they're even? Well, I can divide them all by 2 evenly. What does that mean? Well, it means that when I divide them by 2, for example, 2 divided by 2 is going to give me 1. It's going to give me another full number, as in no decimals, no fractions. Now note, because our domain is integers, when I say number, I really mean integer. So it's going to give us another integer. 4 divided by 2 is going to give us 2. 6 divided by 2 is going to give us 3. And so the question is, how can we generalize this? Because we can keep going forever. Well, you can say, these are my even numbers. I can represent an even number with a variable. I'm just going to represent it with s. And then how do I know s is even? Because I can divide it by 2. And when I divide an even number by 2, I get another integer. And how can we represent these integers instead of writing what they are? We can represent them with another variable. Let's say k. Now we have a general description of what's happening here. But the goal is to explicitly define what it means for a number to be even. So we want to get s by itself. So here we have s divided by 2 is equal to k. And if we want to get s by itself, well, we have to get rid of this fraction, this 2 here. So I would just multiply by 2, cancel out this 2, so this goes away, but whatever I do to one side, I have to do to the other as well. So at the end of the day, we're left with an even number s is equal to some other number, k, multiplied by 2. And again, by number, I mean integer, because that's the domain we're living in. So we managed to explicitly define what an even number is. This is the definition of an even number. But we can't just write this on our paper and leave it as that, because if someone just sees this, they're going to be like, what is s? What is k? Like, what is this? You have to explicitly use words. So in words, this translates to an integer s, so an integer s is even if and only if, so we have to add if and only if anytime we write a definition, there exists another integer k. So some other integer, we call it k, such that if you multiply k by 2, you get s. You get your even number. So this is the formal definition of an even integer s. But we can simplify this definition by using the symbols that we have learned in class. For example, we know that if and only if can be replaced with a double implication, because that's what the double implication means, if and only if. We also know there exists can be replaced by the quantifier there exists. And we can say there exists a k where, so this little comma means where, that k is an element of, so this means it's an element of, it's inside, it's part of, and instead of integer we say the set of all integers. And instead of such that, we can replace that with subject to, so s dot t. This condition where s has to be equal to some other integer k times 2. And then we can move things around so that they're nice and compact. And there we have a nice simplified and less wordy definition of an even integer s. Now, because we have all of the definitions that we need, we're ready to start the proof. And I always like to define the method that I want to try first at the top of my paper. So I say proof by, and the method, in this case, we're going to try a direct proof. And the reason why is because I see an implication. So why is it that when I see an implication, you always want to try a direct proof first? Well, because a direct proof says, let's say that this is P, proposition P, and this is proposition Q, then you assume P to be true, and then using definitions, axioms, theorems that have already been proved, known equivalences, you get to the other side, you show that Q is true. Now, 2 clarifications. Notice that I said try direct proof. Sometimes you're going to get stuck and you're going to have to try another method. Number 2, notice how I said these are propositions, but remember in the first video that we ever did, we said that propositions cannot contain undefined variables. But these variables are defined because we're defining them as integers. These numbers here that are even, or allegedly even, we're going to prove this, are part of the set of all integers. So that's why these here are propositions. They're not predicates. sides. Now let's get started. So again, with a direct proof, we start by assuming P. What is P? N is even. So we assume N is even, but what does it mean for N to be even? Well, we have a definition about what it means for an integer to be even. An integer is even if and only if there exists a k such that that k is also an integer, and it's subject to the condition that if you multiply that k by 2, you get that integer. So in this case, N is that integer that we're assuming is even. So if N is the integer that's even, then there exists a k that is an integer that is subject to the condition that if you multiply k by 2, you get N. So if we assume N is even, that implies N is equal to 2 times k. So it implies that N is equal to 2 times k, where k is also an integer. And what did we use for this step? We used the definition of an even integer. So you have to write down everything that you use. And I'm just going to move everything to one side here. But here's the thing. We assumed P, but we want to get to this side. We want to show Q. But Q contains N squared. So the idea is we want to go from here and we want to say something about N squared. But the question is, how do we go from just N to N squared? Well, we can literally just square the N, but whatever we do to one side, we have to do to the other. So we're squaring one side, but we also have to square the other side. It's still equivalent because we did the same thing to both sides. Now we're saying something about N squared. But if we want to say that N squared is even, again, what does it mean for an integer to be even? Well, if that integer is N squared, if that's even, then there exists a k that is an integer that is subject to the condition where if you multiply k by 2, you get N squared. In other words, to prove that N squared is even, we have to show that there is some integer times 2 that gives us N squared. So we have to get N squared to be of this form. But right now we have N squared equal to something squared. So to get this to look like this, we can try simplifying. So 2 squared is 4, k squared is k squared. And so we have N squared is equal to 4k squared. I just call this algebraic manipulation. That's what these steps are. So now I have N squared equal to 4 times k squared. But again, in order to prove that it's even, I have to get N squared to be equal to 2 times something. So I need a 2 outside. And luckily, I can factor out a 2 from this. So I can take out a 2, and then this is just going to be 2k squared, is 2 times 2 is 4. And so N squared is now equal to 2 times something. So again, this is algebra. So we basically have N squared in this form where we have 2 times something, 2 times something. But that something should be an integer. So what we like to do is recognize that if k is an integer, which we specified right over here, and we're squaring an integer, which is just a fancy way of multiplying it by itself, we're still going to get another integer. We can call it L. And if we multiply that integer by 2, we're going to get another integer. Let's call it R. But how do I know that R is an integer? How do I know that L is an integer? Why can't they be decimals? This is due to something called the closure property of integers. So let's go and see what that's about. So let's say you have a house and that house has a door. So let me draw the little door here, and that door is closed right now. And this is a house of integers. So all of the integers live in this house. So 1 is in here, 2 is in here. And the idea is if I do 1 plus 2, that's 3. 3 is also an integer, so it lives in the house of integers as well. If I do 1 minus 2, I get -1. -1 is also an integer, so it lives in the house of integers. If I do 1 times 2, I get 2. 2 lives in the house of integers. Now, what if I do 1 divided by 2? Well, that's 0.5, 1/2. But 0.5 is not an integer, it's a decimal. So the way that I remember this is, well, 0.5 can't live in this house because it's a decimal, so the door needs to open so 0.5 can get out. Otherwise, the door remains closed. So we say that integers are closed, the door is closed under addition, subtraction, and multiplication, because with addition, subtraction, and multiplication, we get integers. So the door remains closed because these integers are allowed to live in the house of integers. They don't need to leave. But integers are not closed under division, because sometimes when you divide two integers, you're not going to get an integer. So that 0.5 cannot live in the house of integers. The door needs to open so 0.5 can get out. So integers are not closed under division, but they are under addition, subtraction, and multiplication. So if we go back up, if we have an integer k, because we know k is an integer, and we multiply it by itself, it gives us another integer we can call L, is because of the closure property of integers under multiplication or under product, because the property says that if you multiply two integers, we know it's going to be an integer. And if we further multiply 2 times that integer, 2 is an integer times an integer is going to give us another integer r by the closure property of integers under multiplication again. So because at the end of the day, this whole thing is just going to be an integer, we can simply say, yeah, this is going to be equal to some integer, and we can call it r, and then we can bring down everything else. We have 2 times r is what n squared is equal to. And we say that we use the closure property of integers under product because this was all multiplication. And then we say where r is equal to 2k squared and where r is also an integer. But now look at what we have. We have that n squared is equal to 2 times some integer. And what's the definition of an integer that is even? Well, an integer that is even is equal to 2 times some integer. So therefore we can conclude that n squared is even because it is of the form of an even integer. Another way to say it is because we found out that this is true, that we have some integer n squared that is equal to 2 times some other integer r, so this side of the implication is true, then this double implication allows us to say, well, if one side of the implication is true, then the other one is also true. So this integer n squared is even, so that's why we can conclude that n squared is even. And that also shows you why we write definitions with double implication, because it allows us to go from one side to another, one side to another. If it was just a single implication, so it would just be if instead of if and only if, then even though we found that there is some integer n squared that is equal to 2 times some other integer, we wouldn't be able to go and conclude that that integer n squared is even because the implication would be one way. We would only be able to go from here to here. Couldn't go from here to here, and so then we would never be able to conclude that n squared is even. So that is why it's important to write your definitions with double implications so you can go both ways. So here we use the definition of an even integer. So with a direct proof, we started by assuming that p was true, and then we got to the other side by using definitions and properties. So we went from p all the way to q, and so we say therefore, that's what the symbol means, and then you just copy and paste what they wanted you to prove. If n is even, then n squared is even. And then you do a little square to say you are done with the proof, or you could do QED.